Okay, so the problem is entropy generation in a wall. You consider a steady heat transfer through a brick wall of a house. So here is your brick wall, and the heat transfer takes place from a high temperature environment, which is inside your house, to a colder temperature, which is the outside. And the problem tells us the thickness is 30 centimeters. So the thickness of the wall is 30 centimeters. On a day when the temperature of the outdoor is 0, here, and the house is maintained in 27 degrees C. So the inside of your house is 27 and the outside is 0. Therefore, a heat transfer takes place. The temperatures of the inner and outer surfaces of the wall are measured to be 20 and 5. So outside is 27, but the wall temperature is 20. And it is the same way you can say from the problem gives you that the outside wall is 5 degrees C. Okay. The rate of heat transfer through the wall, this Q dot, the rate of the heat transfer is 1035 watts. Okay. Determine the entropy generation, this term, okay, in the wall, and ignore this part of the problem. So let's say the problem asks us determine the entropy generation in the wall. Okay. So this term, entropy generation term, is in our energy balance equation for entropy balance. The entropy balance equation. Okay. And in this case, since the problem tells me steady, it helps you to understand that you need to use the dot forms, the rate form of the entropy balance equation. And so this was the rate form of the entropy balance, right? In this case, since it's steady, then this term here goes to 0. Therefore, what we only left with, the entropy getting in minus the entropy getting out plus the entropy generated should be equal to 0. Okay. So let's see what is the type of entropy getting in. So heat energy and mass carries entropy with it. In this case, we don't have any mass, but there is heat energy flowing through the walls of the brick wall. And so if we assume basically the walls of the brick wall are the boundaries of our system. Okay, so the wall itself is our system. Okay, the wall, the surfaces basically of the wall, outer surfaces of the wall is the system boundaries. And through the boundary, what is crossing is the heat energy. So when the heat energy is crossing, that means it carries entropy with it, remember? So that means what is getting in, what type of entropy is getting in, is the heat, rate of heat over the temperature of the boundary that is getting in. The same thing, the same entropy is getting out, right? Q dot over T, which is the T is the constant boundary temperature. But remember that temperature has to be in Kelvin scale because it's thermodynamic temperature scale. So, okay, so what do we know in this equation? We are asked to calculate this entropy generation, the rate of entropy generation. Okay, so what we can do, actually, I think the problem should have told us the rate of entropy generation. I think there is a wrong wording over there. Let me check my book. Yes, it actually says the rate of entropy generation. Okay, so then now Q dot is given to me. It is 1035 watts. So in this case, that is the same thing is getting in through the boundary one side, and that is getting out also through the other side. So here 1035 watts over the temperature of that surface, which is 20, but I need to add 20 plus 273. Okay, 293 Kelvin. Don't forget to use the Kelvin scale here. Okay, the same minus Q dot is 1035 watts over now 5 plus 273. Okay, 278 Kelvin. Okay, so that's the case, plus the generated entropy rate of generation, and is equal to 0. Okay, so then from this equation, very simply you were able to figure out the rate of entropy generation.